Okay, in this video I'm going to continue on with my tutorial series on thermodynamics and statistical mechanics. This is video number 31 and I'm going to continue on with the third law of thermodynamics. So the previous video to this of course is number 30 where I introduced the third law of thermodynamics. Now in that video I said the following. I said that at T is equal to 0 or 0 Kelvin both the entropy and the heat capacity at constant volume are 0. And we got this expression here that the change in entropy was equal to the integral from your initial temperature to your final temperature of C sub V to T over T. And we also, I said, but I didn't prove or anything, that at low temperatures we have a thing called residual entropy, where some of the states just they don't actually get into the multiplicity of 1. You might have a slightly larger multiplicity, which we won't worry about here. What I'd like to do is talk a small bit more about entropy. So historically the relation ds is equal to q over t was the definition of entropy. That was the definition of entropy, okay? And for many purposes that's the one you can use and you're just fine. Now remember, of course, q, with the reason we have q there and not u is because we're talking at no volume change, or the change of volume is 0 or no work is being done. So let's just, I think it's best to follow this by an example. Let's say that we have, we have two bodies A and B together, A and B together, like this, and we have them at different temperatures. So let's say this one here, A is at 200 Kelvin, and this one here is at 100 Kelvin. We put them in contact with each other. Now we know at this stage that heat is going to flow. We know it for many reasons. We know it because that one is a greater temperature. Temperature is a measure of the how the flow of spontaneous energy. We also know that at a lower temperature, the one at lower temperature is going to have a shallower less del U graph as well. We know that. But anyway, so look, we can accept at this stage that energy in this case is going to flow from B into A. So let's look at the entropy. So let's say, for example, that in total 1000 joules flows. 1000 joules flows, we'll say, right? So therefore, ds is going to be the following. We're going to get that we'll say delta S for the first body is going to be equal to 1000 divided by 200. Now, sorry, that's because the reason it's negative is because this one has heat flowing. There's heat flowing from A to B, so the entropy is flowing out of A, and this should be 200, not 2000. Okay, and of course the answer here is going to be minus 5 joules per Kelvin. Joules per Kelvin. Now if you look at the change in entropy for solid B or system B, we're going to have plus 1000 joules this time, and we're going to have a temperature of 100 joules, giving us plus 10 joules per Kelvin. Now the energy is flowing from A to B, but 5 units of entropy flowed out from solid A or system A, but 10 units of entropy flowed into system B. So in the process of transferring energy, entropy was created. We were after creating additional entropy to that which was already in A and was passing into B. So how do we try and imagine this? It's like saying, it's like a balloon. Your balloon, your balloon will change size whether it is depending on the pressure outside. So if it's going from a region of from a region of high pressure to low pressure, it will arrive in the region of low pressure bigger. Okay, so let's say we have high pressure, so that's P, and this is small p for low pressure. The balloon here might be this size. Might be this size, and it might be this size when it gets here. Okay, so we can use this analogy for entropy. So we can say that this one is hot and this one is cold. So this is B and this is A. And it means that if we sent 5 units of entropy from A to B, but 10 units of entropy arrived at B. So the entropy actually gets bigger. Alright? So whenever energy leaves the system in the form of heat, it's required by law to carry some entropy with it in the amount of Q over T. Okay, that is the amount of energy which it must. So the entropy that is carried by the heat is more when it arrives at the cooler body than when it left the hotter body. Alright? So finally I'll say that only in the limit where there is no temperature difference between the two objects will no new entropy be created. But then there's no heat going to be flowing anyway, so that's not really a big deal. So like I said, in this limit there's no tendency for heat to flow in the first place. So basically what we're after saying here, it's that fundamentally the net increase in entropy is the driving force behind the flow of heat. So I'm just going to write that in words, that the net increase in entropy is the driving force behind heat flow. Right? Thanks for watching. Please pass it on to your friends, subscribe to my channel, and if you're in a good mood, you might also click on an ad. Thank you.